Okay, let's verify Green's theorem for the region I've sketched here and the function we've given here. Now let's look at the region. The region is just a triangle. It's just a triangle from the origin to the point 1, 0 to the point 0, 1. The curve is going to go around the triangle in the counterclockwise direction. We can break the curve into three segments, one segment from here to here, another from here to here, another from here to here. Let's parameterize each of these segments separately in terms of t. Along the first segment, x is going from 0 to 1, while y remains 0. So we let x equal t, where t is going to run from 0 to 1, and y is going to remain 0. Along the second curve, we see that y equals 1 minus x, but if we're going to parameterize this, we want our parameter t to start at this point and end at this point, so we want x to equal 1 when t equals 0 and x to equal 0 when t equals 1. We accomplish that by letting x equal 1 minus t. 1 minus 0 gives us 1. And when t equals 1, 1 minus 1 gives us 0. So x will go from 1 to 0. Y, on the other hand, goes from 0 to 1, and it does so linearly. So we can parameterize C2 as we see here. C3 is just along this part of the curve, is just this section of our boundary, and y goes from 1 to 0. Now we're going to, just to avoid confusion, let's let t go from 0 to 1, so that in order to get y equal 1 at this point, y should equal 1 minus t, so that when t equals 0, y equals 1. When t equals 1, we're going to have y equals 0. Now Green's theorem tells us that the integral over closed curve of f dot ds can be expressed as the integral over that curve of m dx plus n dy, where f is the function mi plus nj, and that this is equal to the integral, double integral over the enclosed region of negative my plus nx with respect to area. And let's just write the fact that f, again, is expressed as mi plus nj, where m and n are understood to be functions of x, y. Now we have a parameterization for this curve, so we're going to be able to set up this integral around the curve. Our m function for any one of these is a function of x. It's just x squared y, so we can substitute the appropriate x squared y for the given parameterization. And before we actually set up and perform that integral, let's go ahead and describe our area region, a region of the plane that's going to correspond to this integral. Now this region is very easily described. We have our triangle, we have our x-axis, we have our y-axis, and just by common knowledge or inspection, we can say that along this part of the curve, y equals 1 minus x. Slope-intercept form, the intercept being 1, the slope clearly being negative 1. So that the region can be described as the region R, where 0 is less than or equal to x, less than or equal to 1, x running from 0 to 1, and for given x, y runs from 0 to 1 minus x. So that an integral over the region is just going to be double integral over the region of m negative my plus nx dA, easily expressed as the integral, double integral, y from 0 to 1 minus x from 0 to 1, of, we'll leave this unspecified for the moment, negative my plus nx dy dx. Now, coming back up here, it's clear that the m function, being the coefficient of the I vector, is x squared y. So we can say m of xy equals x squared y, and n of xy being the coefficient of j is negative 2x y squared. So we can easily evaluate this integral. This is just going to be the integral from 0 to 1 of the integral from 0 to 1 minus x of my. Now my is the y derivative of m. That's clearly going to be just x squared plus nx. It's negative my, so let's be careful about that. Negative x squared plus nx, and nx is negative 2y squared. Integrating first with respect to y, we get negative x squared y minus 2 times y cubed over 3 evaluated between 0 and 1 minus x. That integrated with respect to x. And that equals the integral from 0 to 1 of what? Okay, this is from y equals 0 to y equals 1 minus x, so when y is 0, we're going to get 0. When y is equal to 1 minus x, we're going to get negative x squared times y, which is 1 minus x. And on this term, we're going to have y cubed. When y is 0, of course, that gives us 0. When y equals 1 minus x, that gives us negative, right, this is 2/3 times 1 minus x quantity cubed. Now I've allowed this next step to appear like magic. We simply do the expansion here. Be very careful about the signs in the expansions. I'd use the binomial expansion for 1 minus x quantity cubed. You're going to get 1 minus x plus 3x, 1 minus 3x plus 3x squared minus x cubed, and multiply that through by the minus 2/3. This is going to give you negative x cubed plus negative x squared plus x cubed. You add all that together, you're going to get this, and when you integrate that, you're going to get some fractions that are fairly straightforward. If you integrate x cubed over 3, you're going to get 1/3 x to the 4th over 4, so that's going to give you negative 1/12. Now I'm just going to write out the negative 1/12 because it's going to be negative 1/12 x to the 4th, but you're evaluating that between 0 and 1, x to the 4th, any power of x is just going to give you 1 when you complete the integral. So you can fill in those steps. The negative x squared is going to give you negative x cubed over 3, and that's going to give you a negative 1/3. Antiderivative of 2x is just x squared, which is going to give you plus 1 when you evaluate it to limits. And negative 1/3 is going to integrate to negative 1/3 x, which between the limits is going to give you negative 1/3. And something is missing here. Yeah, I got careless. I had my negative x cubed here, which should have been multiplied through by negative 2/3 and not negative 1/3. So I should have 2/3 here, and that should give me 2